Thank you. Somehow I can't, the remote doesn't work correctly, or I can't make it work correctly, so I'm going to have to walk back and forth. So this is based on two long papers with Miranda Cheng and John Duncan, a shorter paper with Samir, and some work in progress with Samir and a student of mine, Janer Nazaroglu. Oh my goodness. Oh, there we go. Okay, so I thought sometimes when you go to a nice restaurant, they bring you a little amuse-bouche to start out with to kind of whet your appetite and show you what the chef can do. So I thought I would also start with this, and while you're awake, force you to go through a little simple calculation. So in this famous letter to Harvey, Ramanujan wrote down, I guess, 17 Mach theta functions, but one that he wrote down towards the beginning, and one of the ones that has been most studied in the literature, is this particular third-order Mach theta function defined by what he called a series in the Eulerian form. And it has a Q expansion, and I've written down the first few terms in this. Now, on the other hand, I'm not deriving this, but I'm just going to say that there are, in papers of Iguchi and Hakami, and in the long paper by Dabelkar, Murthy, and Zagye, you can find a variety of Mach modular forms. And there, in particular, you can find the first component of a two-component vector-valued Mach modular form that's derived using the sort of techniques that Samir described yesterday. And it has a Q expansion, which has, there's a wall factor of 2, a Q to the minus 1/12, and then this series of terms. Now, to try to give you some idea of what, well, the problem with moonshine is nobody understands what it is, but that is fundamentally what's going on. But to give you an example of the sort of calculations and manipulations, you look at these coefficients, and at some point, you realize that these are related to dimensions of representations of a particular group. This group goes by the name of 2.M12, and what that means is that the group is a group with a Z2 normal subgroup, and the quotient by that Z2 is the group M12, which is a particular kind of sporadic group known as the Mathieu group. I won't tell you its definition, but it's a subgroup of the permutation group on 12 objects defined by some particular conditions. And I've listed part of the character table of this group. So there are 26 different irreducible representations, and there are 26 conjugacy classes of elements. And so this first column, 1A, simply means the conjugacy class of the identity element. And these are the characters, that is, the traces of these elements in the various representations. So the first representation is just the trivial identity representation, where every element of the group is represented by the identity. And 1A is just the identity element. So in this one-dimensional representation, you get 1. Then these numbers in this first column are then just dimensions of the representation. So there are two 11-dimensional representations, there are two 16-dimensional, one 45-dimensional, a 54-dimensional, three 55-dimensional representations, etc. So the first thing to notice is that the numbers 16, 55, and 144 occur in this list as the dimensions of irreducible representations. 330 does not appear in this list, but 330 happens to be 55 plus 99 plus 176. So it's a sum. And if you keep going along this, you can decompose these into sums of irreducible representations. Of course, 16 is also 16 times 1, so this does not uniquely define a way to do it. But all right, so but for the leading coefficients, it's fairly obvious what 1 is supposed to do. So now let's consider the following manipulation. Take each one of these numbers. The first is 2 times minus 1, then 2 times 16, 2 times 55, and replace this number by the representation of the group with that dimension that's suggested by this decomposition. So the minus 2, the 2 times minus 1, I can think of as the trace of the identity element, the 1A conjugacy class, in 2 copies of the one-dimensional representation, up to a minus sign. So now what I do is I twist this by, instead of considering the identity element, I consider the conjugacy class of elements of order 2 called the 2B conjugacy class. So in this group, there are 2 different conjugacy classes of order 2 elements, 2A and 2B. And in 2B, in the one-dimensional representation, of course, you just get 1. So minus 2 just goes to minus 2. Now, in the 16-dimensional representation, you have 2 times 16, and you really should think of that as a sum of 2 16-dimensional representations, chi4 and chi5. And the trace of the 2B elements are 0. So you replace this coefficient 16 by 0. 55 turns out to be twice this chi9 representation, and the 2B trace gives minus 1. So you replace the 2 times 55 by minus 2. And you keep doing that. You decompose this, and then you use the character table to replace the dimension by the character of the 2B element. And if you do this, you can go out as long as you want, you find that this Mach modular form twisted by this 2B element is up to a factor of minus 2 and q to the minus 1/12th, precisely this third order Mach theta function as a function of q squared. So hidden within this probably most well-studied third order Mach theta function is some bizarre connection to the representation theory of a sporadic group. Well, 2.m12 is not a sporadic group, but m12 is a sporadic group. So this should whet your appetite. There's something, I mean, this is a kind of strange set of manipulations. You might say that getting this still does not completely determine how to do these decompositions, but the point is you can do similar decompositions for any of the conjugacy classes, and you always land on Mach modular forms. And I'll give you some details of that later on. So this is an example of this kind of bizarre thing that's going on here.
The 2.m12 is not a subgroup of M24.
2.m12 is not a subgroup of M24, that's right.
If you take a second component and perform the same operation,
you get a different Mach modular form. I mean, in general, you get, so this is a 2-component Mach mod. I wrote down the first component of a 2-component Mach modular form. When you consider these twisted elements, you get a 2-component Mach modular form, but it's on a smaller subgroup than SL2Z. It's on some congruent subgroup, typically. So I want to start by saying a few words about moonshine as it has been understood kind of classically. This is a subject that goes back something like 20 or 30 years now. And I think mathematically it refers to something a little bit different than the way I'm using the term, but I want to use the term to refer to some mysterious and only partially understood connections between modular objects, finite groups, string theory, and some kind of algebraic structure. So the original example of this structure was Monstrous Moonshine, and I'll just say a few words about this. So in Monstrous Moonshine, there's a well-understood example of each of these objects. So the group, the finite group, is the largest sporadic group called the monster. It has something like order 10 to the 50 elements. It's the largest, not the largest finite group, but the largest sporadic finite group. The modular function is the the weight zero modular function j of tau. And there are other objects, which I will describe a little bit more, which occur by doing the same kind of construction that I just discussed, where you take representations and replace them by characters of particular conjugacy classes that give analogs of j of tau called Haupt modules. There's an explicit construction of string theory of a conformal field theory that has the monster as its symmetry group. And that construction was found by Frinkel, Lepowski, and Merman. And it consists of taking a compactification either of the bosonic string or the heterotic string on well, for the heterotic string, it would just be the left moving degrees of freedom. Let's say we consider the bosonic string. We could compactify the bosonic string down to 2 dimensions on a 24-dimensional torus, which you get by taking R24 and quotienting by a 24-dimensional even self-dual lattice called the Leech lattice. And then you do an asymmetric orbifold where you twist just the left-moving degrees of freedom. So that asymmetric orbifold defines a conformal field theory. And in that conformal field theory, there's an algebraic structure given by taking the operator product expansion of the vertex operators of that theory. So this algebraic structure has the monster as its symmetry group and the modular function j of tau as its partition function. So in a little more detail, you can take the upper half plane plus the point at infinity, and its quotient by SL2Z has a fundamental domain, which I think is familiar from various string theory textbooks. And you can map this fundamental domain to the Riemann sphere, and the function j of tau is the function that does that. And it has this expansion with a pole as you go off to I infinity. And then, as Samir mentioned yesterday, the first coefficient here is also 196883 plus 1. And these are the dimensions of the first 2 irreducible representations of the monster. This was first noticed, I think, by John Mackay. And the higher coefficients also have nice decompositions. And in the asymmetric orbifold construction that I mentioned, the function j of tau, so without the constant term here, is simply the trace of q to the L naught minus c over 24 in this particular conformal field theory. Now, one remarkable, and I think, understood precisely mathematically, but not understood perhaps conceptually, is the fact that if you do the kind of procedure that I went through in that opening slide, and you take the representations suggested at each conformal weight, and then you compute the character of some element g in the monster to get these so-called Mackay-Thompson series, that these are also analogs of j of tau in that they map not the fundamental domain of SL2Z, but rather the fundamental domain of certain subgroups of SL2R, discrete subgroups of SL2R, where the fundamental domain is also genus 0. And these genus 0 subgroups of SL2R will play a role later on as well. So this was this fact that all of these twisted things are Haupt modules was proved by Borchards, but I think there's still a lack of a really conceptual understanding of why that is. So,
Sorry, Jeff.
Yeah.
How is that map specified from sphere to sphere that you have on your slide?
Well, you have this fundamental domain, and you need to make it's some set of union of fundamental domains of SL2Z, and you need to patch these together according to the identifications that you get of the boundaries, and then add in some finite number of points, which are the cusps, the images of I infinity. So these analogs of j of tau are basically an instruction on how to do that mapping from the tau region specified by the fundamental domain for this group to a space which is topologically a sphere. Is that? So the development of this monster conformal field theory by Frenkel, Lepowsky, and Merman, and the proof by Borchards introduced a lot of technology into mathematics and string theory. So, for example, although orbifolds as limits of Calabi-Yau spaces were developed by physicists, actual Frenkel, Lepowsky, and Merman were slightly preceded this, but they were doing a special kind of orbifold, which is an asymmetric orbifold and not related to a Calabi-Yau space. But still, they had the basic technology, including modular invariance, twisted sectors, and projection onto invariant states. But they didn't have the same intuition, but they developed the machinery of how to do that. And again, string theorists have the idea of operator product expansions, but mathematicians axiomatized this and formalized it into a theory of vertex operator algebras, which has been very influential in mathematics. So I'm not going to say more about Monstrous Moonshine, although I guess in the discussion section I'd be happy to answer questions about it. Instead, I want to say a little bit about a new kind of moonshine relating K3 in the Matthew group that was discovered in 2010 by Oguchi, Oguri, and Tachikawa. And there will be other talks about this, and so I won't maybe go into a lot of detail, but I'll say a little bit to try to kind of set the stage. Then I want to talk about an extension of this called Umbral Moonshine, which is this work done jointly with Miranda and John Duncan. And then I will talk a little bit about some attempts to relate both Matthew and Umbral Moonshine to something that is more physical, namely black holes, BPS state counting, and the conformal field theory describing 5 brane configurations. So it's sort of a mathematical part of it, and then there's some attempt to relate this mathematics to something in string theory. And please ask questions, because between the amount of time I'm allotted this morning and the semi-infinite amount of time this afternoon, I think there's plenty of time for questions, and I would prefer questions to confusion. So please, yeah, ask away. Okay, so I will be a little bit, maybe go a little fast over this, but just to say a few things. And Samir also covered some of this. So a K3 surface defines a 4,4 superconformal field theory with central charge 6. And there's this quantity known as the elliptic genus, which is defined by a trace in the Ramon sector, which I think Samir described. There's a U1 weighted by a U1 charge, and this actually turns out to be a holomorphic object because all of the states that contribute have L0 bar equal to a quarter. So the standard modular properties of one-loop integrals in string theory, along with spectral flow, can be used to show that this is a weak Jacobi form of weight 0 and index 1. And this has a space-time interpretation in terms of the index of the Dirac operator, or kind of generalized Dirac operator coupled to various powers of the tangent bundle of the manifold. And so it's independent of the moduli and can be computed directly in an orbital fold limit, but it can also be computed using a kind of indirect argument, which I'll just mention. So these are, I think I can skip over this because this is exactly what Samir went through. These are the modular and elliptic transformation properties of a Jacobi form and the condition that it be a weak Jacobi form, so that's completely standard. And Samir also discussed the structure of the ring of weak Jacobi forms. Here I've written down that structure just for k even, which is all I need in this argument. So there are 2 generators, this phi 0, 1 of weight 0 and index 1, and phi minus 2, 1. And here are the expressions, which I hope agree with Samir. And then you can multiply by arbitrarily modular forms. And if you want to get something that has weight k and index m, then you have to combine the weights and the indices so that everything adds up correctly. And just a few examples, which will play a role later on. So at weight 0 and index 1, there is a unique Jacobi form. So up to an overall constant, there's just a one-dimensional space here. At index 2 and weight 0, there are 2 possibilities. You can take phi 0, 1 squared, or you can take phi minus 2, 1 squared and multiply it by E4, and that also will have weight 0 and index 2. And then at index 3, there's a 3-dimensional space. So at weight 0 and index 1, you have a 1-dimensional space, and since the elliptic genus of K3 has to be a weak Jacobi form of this weight and index, all you have to do is to determine the constant in front, which you can fix by the fact that the elliptic genus at z equals 0 is the Euler number. So that gives you the elliptic genus in terms of this one weak Jacobi form. And then since there's a n equals 4 superconformal algebra at play, you can decompose this elliptic genus into characters. These are characters in the Ramon sector. And there are 2 classes. There are so-called massless characters, which give rise to massless states in space-time. The character is a complicated Appel-Lurk sum, which I'm not going to write down. And then there are massive characters where h is greater than a quarter and L is equal to a half. And they have a fairly simple expression in terms of the odd theta function squared divided by eta cubed. So if you decompose into n equals 4 characters, you find a combination of massless characters and then an infinite sum of massive characters. The coefficients multiplying this infinite sum of massive characters I've called C of n minus an eighth, and they have the following values. You get 45, 231, 770, 2277, etc. And the observation of Iguchi, Oguri, and Tachikawa is that these numbers are all dimensions of irreducible representations of M24. M24 is another sporadic group discovered by Matthew. It's a subgroup of S24, the permutation group on 24 objects. It's not nearly as big as the monster, but it's still not too small. I think it has sort of 1 billion elements, rather than 10 to the 50, or maybe 10 to the, well, actually more than 1 billion, maybe. I forget whether it's 10 to the 9 or 10 to the 12 or 10 to the 13. But anyway, it's, you know, some reasonably large group, but not nearly as big as the monster. So, as in this first little example I gave you, you can try to take these coefficients and decompose them into irreducible representations of M24 with some positive integer multiplicities. This is not unique without some further information, and that further information comes from the kind of procedure that I described in the first slide. You consider these twisted versions and demand that they have some modular properties.
But 200 million.
Sorry?
It's 200 million.
200 million. Oh, that's really quite small then. So you can repackage the decomposition using a particular identity relating massless and the kind of limit of massive representations as h goes to a quarter. And when you repackage it that way, you can write the elliptic genus purely in terms of this massless character and then this massive character multiplied by a function of tau, which I call h2 of tau. And this object is a Mach modular form of weight 1/2, which Samir wrote down for you in a different form yesterday. So the fact that these coefficients are related to representations of M24 is reminiscent of this monstrous moonshine for the modular function j of tau, except now there's something different going on because there's a different group, and instead of a modular function, we have a Mach modular form.
Jeff,
Yeah.
I get confused by the following fact. I mean, we know H2 is Mach, and we know we can make it modular by adding, these like Samir said yesterday.
Right.
But out here on the right-hand side, we have, that's a Mach object.
Yes.
And so by the left-hand side, everything is holomorphic on this thing.
Right.
And the elliptic genus is a nice modular object.
Right.
So, how does this is not a completion or anything, right?
No. So what this is actually is both of these terms are Mach. This involves an Appel-Lurk sum, which Samir described as being a Mach modular object. And instead of a completion, this is really a sum of two Mach modular things whose Mach modularity cancels each other out to give something that's modular.
Actually, the reason I'm asking this question is related to the question yesterday, which he was bringing up, multiply things. So you look at the massless character, so you can multiply the massless characters. For instance, let's just say this is the level 1 massless character. You will discuss the level 2 guy. If you take the square of this thing, that will look, that behaves nicely, and you can show up to other massive pieces. These two are equal to each other. And I wonder if there is some meaning in this. So even though we cannot multiply, Mach modular forms, we can multiply characters. We know that.
Yes, but the characters are not Mach. They are made of a piece which is Mach.
Yes.
Right.
Which is actually making it fun. The character is a perfectly holomorphic object.
Yes, I understand. So
And in the right-hand side as well.
Yeah, so there is something I want to say, I think, in the afternoon, which is not exactly that, but perhaps is related to it, because we will see that analogous to this H2, that there are some HMs with M taking a bunch of values, and there are some relations, for example, between H H4 and H2, H8 and H2, H9 and H3. Basically, there's some kind of multiplicative structure when this integer m is a multiple of some other value for which there's a moonshine. And it's not quite the same, I think, as what people have discussed, but it does indicate that there's some kind of multiplicative number theoretic structure going on. And maybe in the context of that, we can renew this discussion and try to understand better what's going on.
That it's much easier to see it at the level of characters, but if you go and start looking in terms of mock objects, the next one is a vector valued object. So, I mean,
right.
Obviously, it's messier.
Right, so the number of components grow, but then the relations seem to involve not just the components, but sums or differences of components and particular twists. So I think there's some kind of multiplicative structure, but it's a little more intricate than you might get just by multiplying characters. So hopefully that can be one of the things that we discuss a little bit more in the afternoon. Okay. So I guess briefly, if we try to contrast these two cases, we have either the modular function or a mock modular function with an expansion in terms of coefficients that clearly are trying to tell us there's some kind of group theoretical structure. For the Monstrous Moonshine, Frenkel-Lapowski and Merman constructed explicitly a conformal field theory that has the monster as a symmetry group. Another way of saying that is that at each value, at each L0 eigenvalue in that conformal field theory, there is some vector space Vm of states with that conformal weight, and those vector spaces carry a representation of the monster, so they're modules for the monster, and then there's an infinite set of those graded by L0, so there's something that they call V natural, which is a infinite dimensional module for the monster. So these coefficients A of m appearing here are the dimensions of these vector spaces. Now, you would expect that there could be a similar structure here, that is some natural infinite dimensional module for M24 with a grading by the power of Q in this expansion, but we don't know who the analog of Frenkel-Lapowski and Merman are because this has not been constructed yet, and we don't know whether it involves a conformal field theory construction, although again, as I will try to say later on in the discussion period, and I think will also come up in some of the talks, there's overwhelming evidence that some kind of conformal field theory structure is going on here, but we don't know exactly what it is. It's natural to think that it's a conformal field theory related to K3, but there's also a proof that no conformal field theory corresponding to K3 has full M24 symmetry. So the answer has to be a little bit more intricate. But in either case, we can define these Mackay-Thompson series by replacing the dimension of these vector spaces here, or of these here, which are the trace of the identity element in that vector space, by a trace of a group element in that vector space, and construct twisted versions of these things.
Sorry, I will make a very little confusion.
Yeah.
I thought that the analog of that order 15 in this case would be the K3 theory, so I guess I'm sorry, because there the J comes out as a partition function,
Right.
and here that is a so.
Right, that's a very natural expectation, but unfortunately there's a proof that there is no conformal field theory that corresponds to a superconformal, a sigma model with K3 target space that has M24 symmetry. And so that can't be the full story. You can find conformal field theories that have some smallish subgroups of M24, and I think Anne and Katrin will discuss an attempt to sort of combine K3 surfaces that have different symmetry groups and combine those into a bigger group, but there certainly is not there's not a particular conformal field theory related to K3 that has all of M24 as a symmetry group.
The difference is that here you just count some states, whereas on the Monstrous Moonshine, it's really the partition function.
Yeah.
So you kind of
Right.
count all the states of your K3
Yeah.
theory.
Yeah, so
Probably gives you more freedom, but nobody knows how.
right, exactly. So just to, if I can, just expand slightly to just make it, so here exactly, you're counting you're not counting with any weighting, so every state contributes positively. Here, you're computing the elliptic genus, which has a trace of -1 to the f. So first of all, the states can cancel, and you're not just computing, positive numbers. And if you look explicitly at certain conformal field theories, like take T4 mod Z2 as an orbital fold limit, then you can explicitly look at what the states are contributing to the elliptic genus, and you can see that they don't decompose nicely into M24 because they're cancellations.
So you wanted differently with the same elliptic genus?
The answer is nobody knows what you want. I mean, there are different philosophies about how to solve this problem, about how to explain M24. And I think a number of the talks here will involve different philosophies of how to solve this. But my opinion, at least, is that nobody actually has an explanation of why M24 seems to be appearing here. And so it's a mystery, as many things are in Moonshine, which is why it's hard to explain conceptually what's going on, because we don't know what's going on. So all we can do is collect facts and try to find, it seems much more subtle than the monster case, and that was quite subtle to understand. So
It's just different. We're starting at the other end. In the monster case, we start with J, and then we construct the CFT.
Yeah.
In the P3 case, we start with the CFT, and we don't really know what to do with this
yeah,
modular form, maybe.
right.
Do these cancellations occur at a generic point in the modular space or spatial point in the generic space?
I think they work at special points in the moduli space, because at generic points you probably don't have this kind of cancellation.
Genus is a partial function, at least for these states.
Well, I don't know for sure, because it's a little hard to do the explicit counting at generic points in the moduli space. I mean, the points where we can actually look at exactly what's going on are Gepner points or orbital fold points.
If you do different orbital folds, presumably the cancellations are different, right? Or
Right, and I think you find different cancellations at different orbital fold points. Yeah.
We'll say a little bit.
Yeah. So, yeah. So you could.
I would just like to re-emphasize what Kathleen said, is that the J function is the partition function of this config theory, least module or something. But H2 is not the partition function of config theory.
Right.
But you're saying it's not even the elliptic genus. H2 is not the, so I mean.
H2 shows up in the decomposition of the elliptic genus, but it's. So I mean, H2 is kind of, well. Yeah. So here's the elliptic genus. Yeah. H2. It's counting the number. Those coefficients count the number of massive representations. With a sign. With a sign. And so it's sort of suggesting that maybe you want some kind of super VOA where you have, something an analog to fermions and bosons, but then, yeah, there's something more intricate going on, but we don't know what it is. This is just what Samir said yesterday, so I don't really have to explain it. That's what a modular form is and what a mock modular form is involving the shadow. So this particular example, as he said, you should also ask what the shadow is, and the shadow of H2 is eta cubed, although I'm going to use a normalization later. You see, there's a constant here, and without specifying without a convention for what this constant is, you can't say what the coefficient in front of the shadow is. So we will use a convention later where the coefficient here should be 24. And the reason it should be 24 is that when we start twisting, 24 is going to play an important role, although I won't go through the details, because M24 has a 23-dimensional representation and a 1-dimensional representation, and that 23 plus 1 being reducible is a 24-dimensional reducible representation, but it's what's called a permutation representation, where every matrix that represents an element of the group in that representation looks like a permutation matrix with rows that have zeros and then one and a 1 someplace. So when you twist, you take that 24 and you replace it by a number which you get by twisting in this permutation representation of M24. Okay, so again, as Samir said, Mach theta functions appeared in 1920 in this famous letter, and here's the start of that letter. And if you ever find yourself in Cambridge, England, I highly recommend getting someone to take you to the Wren Library, because in the Wren Library you can ask them and they will bring out this little box, and the box has hundreds of pages of paper in Ramanujan's handwriting, and you can read this and look at them, and it's kind of a wonderful experience. So in this Matthew Moonshine, we have a triple of objects. We have a Mach modular form, we have its shadow, I've now put the 24 in, and we have a finite group that seems to act on the coefficients of this Mach modular form and this coefficient of the shadow. So one obvious thing to do is to try to generalize this structure using string theory ideas by replacing K3 by some other kind of Calabi-Yau manifolds and looking at elliptic genera. But so far that has not, there's some interesting results, but it has not led to a vast generalization of this story. On the other hand, there does seem to be a vast extension of this, but with an interpretation in string theory which is still obscure or non-existent or whatever. And this is what we call Umbral Moonshine. So it required a lot of sort of digging around and some borrowing of results from Dabelkar, Murthy, and Zagier, but the answer is yes. This is the first of actually 23 different examples where all of this structure is there and more. And I don't know where the structure is coming from, and that's one of the things that I will mention in the discussion section. So I can't tell you why it's there, but I can tell you what the structure is that we uncovered. And this very much has the feeling, that we all have, that sometimes you find something and it's not like you invented it, you discovered it, because once you find one piece of it, you keep digging and you find more and more and more. And this is very much like that. So at least mathematically, the organizing object seems to be a quantity that I will call X. X is a root system with A, D, E components, rank 24, and with all components having the equal Coxeter number. And so perhaps I should just remind you. So the simplest example would be A2 or SU3. And the root system there are two simple roots, and then when you take linear combinations, so this is a rank equals 2. This is the roots define a two-dimensional lattice. And if this alpha 1 and alpha 2 are the two simple roots of A2, then you can consider a reflection in alpha 1 followed by a reflection in alpha 2. So if I take, I don't know, let's say, if I just take this guy here, and I reflect it in alpha 1, I go down here, and then if I reflect it in alpha 2, I go over to here, and that corresponds to a 120-degree rotation. So this is a rotation by 120 degrees. That is, it's order 3. Product of two reflections is not a reflection, it's a rotation, and it's a symmetry of this, so that makes sense. It's order 3. And this is called the Coxeter element. So in general, the Coxeter element is the product of reflections in the simple roots, and the Coxeter number is the order of this Coxeter element. So in this case, the Coxeter number for A2 is 3. And this has obvious generalizations to root systems of A, D, or E type. So take something that has components that are made out of A, D, and E root systems with total rank 24 and with all the components having equal Coxeter number. It turns out that there are exactly 23 such root systems. You can take 24 copies of the A1 lattice, 12 copies of the A2 lattice, 8 copies of the A3 lattice. When there are more exotic things like A11, D7, E6, and then you kind of go up to E6 to the 4th and E8 cubed. So for each one of these 23x, we, being Miranda, John, and I, claim that there exist 6 mathematical objects that are determined by x.
MTX.
Sorry?
What about MTX? Do they also associate 6 objects?
Well, we spent many weeks debating this question because MTX you would presumably like to think of as the Leech lattice. But we couldn't really find a convincing mathematical sense in which the Leech lattice was a natural generalization of all of this. So we omitted this possibility. But it's possible that in a as I'll mention later some connections between Monstrous Moonshine and Umbral Moonshine. And I think it's certainly possible that in an eventual understanding of this story that the Leech lattice should be included in this in some way, but we didn't feel that there was enough evidence to include it right now. So we don't. But I think that may be something for the future. So these things have these labeled by X, H, S, G, T, gamma, T, and L. So I need to explain a little bit what each one of these guys is and what they have to do with moonshine. So the first thing that you can associate to X is a Niemeyer lattice. So recall that even unimodular, self-dual, positive definite lattices occur only in dimensions that are multiple of 8. And the first 2 examples of these we are all familiar with. There's the E8 root lattice, and then there's the E8 times E8, or spin 32 mod Z2 lattice that appear in the construction of the heterotic string because they are the 2 even self-dual unimodular lattices that give rise to modular invariant string theories. And then in dimension 24, there are 23 even self-dual lattices. And then there's the Leech lattice with no roots. And when you go up to dimension 32, I think this number explodes. And I don't remember what it is, but I think there's something like 10 to the 5th or 10 to the 7th or something. I mean, it goes completely crazy. So this is kind of an interesting case, which is the last set of even self-dual lattices where there's a manageable number and things haven't completely gone crazy. So it's a classical result that each Niemeyer lattice is uniquely determined by its roots, that is the points of length squared 2, and that those sets of roots are in 1-to-1 correspondence with what I've called X. Now, that does not in general mean that the Niemeyer lattice is the same as the root system. There's one case where that's true. So if I take the E8 lattice, that's an even self-dual lattice. And if I take 3 copies of that, that's also even self-dual. But if I take A1 to the 24th, that is not an even, that root lattice is not an even self-dual lattice. So what you need to do is you need to add in certain weights in such a way that you construct a self-dual lattice. And there's a complicated way to do this. It's called, there's a glue construction and a glue code, and you can read about the details of this in the famous book by Conway and Sloan. But the basic idea is that you keep adding in weights in according to a certain rule in order to form an even self-dual lattice. And there's a proof that starting with these 23 x's, you can do that. So the first thing you can construct from this data is a 24-dimensional even self-dual lattice and Niemeyer lattice. The second thing is a finite group G. So for each Niemeyer lattice, we define a finite group. There is always a Weil group, which is the group generated by the reflections in the roots of the ADE components. So in this case, the Weil group is generated by reflections in alpha 1 and alpha 2. And those Weil group transformations if we considered string theory compactified on a 24-dimensional lattice, which was R24 mod the Niemeyer lattice, those transformations would be discrete elements in the gauge group. But in general, there's an automorphism group of the lattice, which is bigger than this Weil group, because there can be symmetries that permute these weights that we had to add in to get an even self-dual lattice. And so you get a larger symmetry group with the Weil group acting as a normal subgroup, and the quotient by that is a group GX that, if we thought in string theory context, would act as a finite global symmetry group of string theory compactified on this 24-dimensional torus. So for the A1 to the 24th Niemeyer lattice, this group is M24. For the A2 to the 12th lattice, this group is 2.M12, which was the group that I discussed in the very first example. For E8 cubed, it's a group S3. And you can find in our paper a list of what these groups are for all of the other 23 Niemeyer lattices. Now, I mean, this might seem a little bit odd, but I mean, so far there's nothing about mock modular forms. There's just this strange connection between groups that we've encountered and automorphism groups of Niemeyer lattices.
Like 2 times M12, maybe you explain that.
Sorry?
What do you mean by 2?
So 2.M12 is related to M12 in the same way that SU2 is related to SO3. Namely, there is a Z2 normal subgroup, and if you quotient by that Z2, you get the group M12. So it's just finite group theorists use this notation to indicate
M12 is a subgroup of M24?
M12 is a subgroup of M24, but 2.M12 is not a subgroup of M24. So it's a little bigger than you get from. Okay, then there are two other objects, a genus 0 subgroup and its Haupt module. So this is a new result, which I guess could have been noticed long, long ago when people were first doing moonshine and looking at these things, but it wasn't. And the fact is that you can use the eigenvalues of the Coxeter elements of the components of X. So here you have a Coxeter element of order 3, and the eigenvalues are just e to the e to the 2 pi I over 3 or e to the 4 pi I over 3, but in general there's some list of eigenvalues. And the eigenvalues of those can be used to define a particular ratio of eta functions in a way that I won't go through in detail, or won't go through at all really. But as an example that something as non-trivial is going on, there are a special set of subgroups of SLT called gamma naught n, where you take an element of SL2Z and you demand that this coefficient C be equal to 0 mod n. These subgroups have fundamental domains which are genus 0 for n equal to 2, 3, up to 9, 10, 12, 13, 16, 18, and 25. And those are exactly the Coxeter numbers of X that have an A-type component in them. And there are similar results for the other Niemeyer lattices, but they involve slightly more complicated subgroups. So this, again, is kind of a bizarre thing. And so we have a construction both of the genus 0 subgroup and its Haupt module, the thing that maps this fundamental domain to the Riemann sphere. Now, yeah.
E of X is Tx, so gamma X is the genus 0 subgroup, and Tx is.
Right. So Tx is an analog of J of tau. And I haven't given you a formula for it, but in our paper, so an example for, I guess m equals 2, that is for gamma naught 2, you can take eta of 2 tau to the 12th, I believe, or eta of tau to the 12th, and either that or its inverse, I forget, is a Haupt module for gamma naught 2. And these powers are related to the fact, I think maybe this is 24 actually. So this too is related to the fact that the Coxeter element for A1 just has order 2. And so for these other cases, again, there are ratios involving eta functions that are the analogs of J of tau. And there's an explicit way of telling exactly what the powers and coefficients are here in terms of the eigenvalues of the Coxeter element of this ADE list. Okay. So let me just mention something which I don't really know whether it's just a curiosity or there's something else going on, but it does play a role in a recent paper of Ken Ono and collaborators. So these Haupt modules occur in 2 different ways. First of all, there's this construction which I didn't really explain to you, but I mentioned that there's a way of taking an X and constructing a Haupt module for each of these 23 X's. On the other hand, in Monstrous Moonshine, you can construct the Mackay-Thompson series where you twist by an element of the monster, and that also is a Haupt module. So in many cases, you can label an example of Umbral Moonshine with a conjugacy class in the monster that gives rise to the same Haupt module. So the A1 to the 24th case that gives you this Haupt module involving a ratio, this is kind of a shorthand for this ratio of eta functions, can be associated with the 2B conjugacy class in the monster, in that when you twist J of tau by the 2B element, you get a Haupt module which is the same as the one that you get from this construction. And so here are all the examples of X's, and then labeled here are all conjugacy classes of the monster that give rise to that same Haupt module by doing this twisting procedure. So each example of Umbral Moonshine corresponds to a conjugacy class in the monster. And that may be important later on.
What's this number? L number 7?
So L is something that we call the lambency, and it essentially labels the genus 0 subgroup. So in all these cases, in the first, where there's an A component, it is labeling a genus 0 group gamma naught of L. In these cases where there's some 2n plus n, it's labeling a genus 0 subgroup that is of the form gamma naught of 2n, and then with the addition of a particular Akin-Lehner involution. And these E6 and E8 examples are slight generalizations of that, where you add some particular additional elements.
Do you understand these frame shapes from any physics?
This is all math at the moment, so no. I mean, there's, no.
Because there's a reason that there's some examples with Ashok Sen and Dilip Jackal looked at, and these are like n equal to 4 orbitals of type 2, this thing. And if you look at the I shouldn't call it it's not Harvey counting. If you do some counting, you get these frame shapes.
Right. So these frame shapes, these frame shapes do. A subset of these frame shapes arise in the physics literature in BPS counting, involving things like CHL models, and so that is potentially a way of understanding physically some of what's going on. But of course, we have many more examples than occur just in CHL, so I think if that is a starting point, one needs some additional structure on top of that too.
CHL. These are not CHL models.
Oh, okay.
The ones I'm talking about.
What are they?
Starting from type 2 on T6, and you just do some asymmetric orbifolding.
Oh, I see. Okay.
And you get
Okay.
So you get n equals 4 symmetry, and if you follow the chain of dualities, it doesn't go to the heterotic string; it comes back to the type 2.
I see.
So that I don't think they have a heterotic group.
Okay.
And so in those examples, we were getting frame some. I mean, only some.
Some. Yeah.
Some of the frame shapes. So eta quotients come, not just
Right.
eta
Right. And is it do you get only genus 0 in those examples?
I don't remember now. We had done some. I mean, there's a paper I wrote with Dilip Jackal.
Uh-huh.
We have some 3-4 examples.
Okay. I guess it would be very nice to understand, if there was a physics explanation of why you got genus 0, that would be very interesting. Yeah.
So, I mean, we thought these things are the Conway group, but
Yeah.
I wanted to ask, these frame shapes are in the, do they appear in the Conway group or are they typical of, do you know? This, some of them, of course, appear in the Conway, but all of them, too many.
I know, well, I can tell you one example that doesn't occur, and it's this one that has the, in parentheses, 25Z. This is, in the original Conway-Norton paper, this is called a ghost element. There's a genus 0 guy, but there isn't a conjugacy class that gives the right thing. There's some weird, yeah, so, I'm sorry, I don't remember, but I don't remember for these other examples what the answer is. There's an answer, but I don't remember what it is, unfortunately. Yeah.
One can see that there's some relation between L and pi x.
Yeah.
And I guess pi x and gamma x would have. What is the relation with x itself? What's the rule starting from some x to get the other three rows?
So the rule is you take x, you look at the eigenvalues of the Coxeter element, and those eigenvalues determine this frame shape pi x. Essentially what you do is you take the you look at the eigenvalues of the Coxeter element, you construct the characteristic polynomial that has zeros at those eigenvalues, and that characteristic polynomial can be constructed from this frame shape. And so that's the basic data that goes into it.
So are there other conjugacy classes of monster which don't appear here?
Yes, I believe there are. Well, yeah, no, there certainly are. There certainly are, because there are more than 23 conjugacy classes in the monster. I think there are 90.
Do you know why they don't appear in this?
No, I don't know why they don't appear, because I don't know why these do appear. The connection is very indirect. There are two ways of obtaining help modules, one from twisting by elements of the monster group, and that gives genus 0 for all elements of the monster. But then some of those help modules arise by the construction that I've mentioned by using the eigenvalues of x. So I don't know whether there's a deeper connection or whether it's simply you have help modules in two different ways, so you can, label them interchangeably. But I think there are some hints that there's more going on, but I don't know for sure. So I mentioned this just because it's possibly interesting, but it could just be a coincidence. Okay, so finally, there is a set of mock modular forms, and their shadows also labeled by x. And I am perhaps not going to go into enough detail on this, but I'd be happy to answer questions later. Samir described to you a way of constructing mock modular forms from meromorphic Jacobi forms. And the construction that he described if you start with a Jacobi form of weight 0 and index 1, and decompose it into characters of n equals 4, that was the K3 elliptic genus construction. But you can generalize it to weight 0 and index m minus 1 Jacobi forms, where you either take these forms and decompose them into representations of n equals 4, or you use them as the starting point for constructing a meromorphic Jacobi form, which you then decompose into its polar and free part. And the free part is a mock Jacobi form. So in their work, they identified a special set of Jacobi forms of optimal growth, and many of their examples exhibit moonshine with groups on our list GX. So just to give you, I think rather than trying to explain more the sort of general construction, I'll give you an example. So the first example beyond the M24 one is where you use for X 12 copies of the A2 lattice, and you start with the Jacobi form, which is a particular linear combination of the two basis elements of weight 0 and index 2 Jacobi forms, which is constructed in order to have kind of the least polar part, or the least negative discriminant in its expansion, in its Fourier expansion. And the group that you get from this Niemeyer lattice is 2.M12. Now, one thing that you'll notice is that this Jacobi form is not constructed from the data of X. And that seems very bizarre and unpleasant to me, because the group is constructed from X. As I'll mention, the shadow is constructed from X. Other things are constructed from X, but the object from which you actually get the Jacobi forms is not directly constructed from X. It's constructed by making a particular choice in the space of Jacobi forms that satisfies some kind of optimal growth condition. So you can either use the procedure that Samir described, or you can simply decompose into n equals 4 characters, where now the massive characters are labeled both by L equals 0.5, and so you get 2 Mach modular forms, or vector-valued Mach modular forms, because the decomposition into n equals 4 characters now has 2 independent components. And you get these 2 guys. The first one is what I wrote down in the very first slide, and the second one has these set of coefficients. And as I mentioned, these numbers 16, 55, and 144 are dimensions of irreducible representations. They're actually irreducible representations of 2.M12, where the Z2 action is trivial. And these coefficients are dimensions of faithful irreducible representations of 2.M12, meaning the Z2 acts non-trivially. So the decomposition into 2 components actually is mirrored in the group theoretical structure, in that the even or odd components have non-trivial or trivial Z2 action for the group.
So it's like going between half integer and...
It's like the difference between integer and half-integer representations of SU2, yes.
Does minus 2 occur as a limiting genus of something
So it does not occur as the elliptic genus of any compact Calabi-Yau space, because if you, so this is a trace in the Ramon sector, but you can use spectral flow to figure out what operators would exist in the Navier-Schwartz and Navier-Schwartz sector, and you find that there's no identity operator. And that's not a good thing for a conformal field theory. But on the other hand, as other people will discuss, there's a lot of evidence that there should be some kind of conformal field theory construction, and I think that evidence will probably go through for these other examples. So maybe we need to look at something more exotic. Maybe it involves non-compact conformal field theories, since those also generate Mach modular forms through their elliptic genera. Maybe you have to do some other kind of construction, but I think that's one obstruction to finding a simple physical interpretation of these other examples, is that none of these Jacobi forms can be associated with elliptic genera of compact Calabi-Yau spaces. So, and how am I, sorry? Okay. So my plan, my secret plan for the discussion section was to make too many slides for the morning and then just keep going in the afternoon. And I think I probably am going to accomplish that. But I also do have just some general questions and discussion points that I'll write on the blackboard. So anyway. Okay, so just a little bit more details of this n equals 3 case. So there are 26 conjugacy classes. So there are 52 Mackay-Thompson series, because you can twist each of these 2 components. So I guess for every card in a deck of cards, there's a Mackay-Thompson series. And most of these can either be identified with eta functions or with the order 3 Mach theta functions that Ramanujan first wrote down. So for example, here was the example I gave you in the very first slide. You get this order 3 guy. Ashok asked what happened if you twisted the other component, and the answer is that you get another one of Ramanujan's Mach theta functions that I think he called, I don't know if he called it or somebody else called it, but it's standardly written as omega. And I haven't written down, but it has a similar kind of Eulerian form expansion. And results of Zweigers can be used to verify the existence of a two-dimensional representation such that this pair defines a vector-valued Mach modular form for gamma naught of 2, which is exactly what you would expect according to this twisting structure. And you can work out what the analogs of these are for all the other conjugacy classes. And in many cases, you get order 3 Mach theta functions. So for, sorry, I'm having trouble with the pointer. So for the 6C, you get something called chi. Here you get something called rho. Here you get something, a linear combination of phi and psi. These are all third order Mach theta functions. But then sometimes you get something that is not Mach, but is rather modular and can be written as a ratio of eta functions. All of these classes are cases where the character of that element in the 24-dimensional permutation representation is 0. So you twist the shadow, and that 24 becomes the character in this particular representation. That character is 0. The coefficient of the shadow is 0. So you have to get something that's modular rather than Mach modular. And you can check that, in fact, you do get things that are modular, that are these ratios of eta functions, which are modular of weight a half for various congruent subgroups that are linked to the order of the element that you're twisting by.
Because that's exactly where the massless character disappears.
Yes, yes, yeah, yeah. When you twist the massless character, that's exactly where it disappears because, yeah, exactly, exactly. So the two examples, m equals 2 and m equals 3, the shadows are proportional to the weight 3/2 theta functions, which are just the z derivatives of this weight a half theta function that I think Samir also wrote down. So for m equals 2, the shadow is proportional to eta cubed, 24 eta cubed with our normalization. And for m equals 3, it's a two-component vector-valued shadow with components S31 and S32. Now, in some cases, one can modify these shadows by a kind of twisting or folding operation. Take the shadow and take linear combinations with some set of matrices and demand that these matrices be such that the modular transformation properties of S are left invariant, and also impose a certain positivity condition, which is kind of, well, analogous to the positivity condition that one uses when one tries to modify the partition function of affine SU2 or minimal model conformal field theories. The mathematical classification of these matrices is exactly what was done in the famous paper by Capelli, Itzikson, and Zubair, where they classified modular invariant SU2, affine SU2 partition functions. And they showed that there is an ADE classification of these matrices. So this raises the following curious possibility. Since there's an ADE classification, we can take an X that determines a Niemeyer lattice and is specified by an ADE root system. It has a Coxeter number M of X. And we can take these shadows S of M and R, and we can twist them in a way that is determined by the A, D, and E components of that Niemeyer lattice. In each case, that leads to a shadow, which we'll call S of X, and that shadow exhibits moonshine for the group G of X, which was constructed in terms of the automorphism group of this lattice. So in our paper, we provide constructions of the Mach modular forms and the shadows for each of these 23x. And we also give the Q expansions up to order something like Q to the 25th of the Mackay-Thompson series for each group, for each conjugacy class of elements of the group G of X. So, well, this is why the paper has something like 190 pages and 120 of them are tables, because there are 23 examples. In each example, you have from 2 to 24 components, and then each of those components can be twisted by the number of conjugacy classes, which ranges from 26 to 2 or 3. So we did all that, and you can find it all in the tables, and this whole structure seems to generalize the M24 structure in that sometimes the groups are kind of small, but we find moonshine, we check the twisting generates Mach modular forms, and there seems to be a vast generalization of what's going on relating K3 and M24, but now without a clear physics interpretation. So if I have had time, which I don't, but I will continue this afternoon, I wanted to talk about one attempt to try to embed this in a physical context, which is this work with Samir on 5 branes. So I think since this is when I should stop, I will stop here. I will start the discussion with a, I don't know, sort of 15 or 20 minute presentation that talks about that, and then get rid of the slides, maybe write some questions on the blackboard and see if I can get people to say things and whatever. But, so let me stop here and I'll answer questions about this part of it.
Thank you. Question?
Yeah, so good.
Very basic, but to understand how we construct h of x, given x. Will that explain the methodology?
No, I did not. So there's not a direct way that I know of constructing hx from x. And that is kind of, it seems to me, an important missing link in this whole discussion, because everything else in this story has a very direct construction given x. It's certainly constrained because you know what the shadow is supposed to be, but just knowing the shadow does not determine the Mach modular form by itself. There is a kind of optimal growth condition, but yeah, and well, there are various ways that one can construct H, but I mean, including both kind of doing searches in the space of these things to find things that have an optimal growth condition, which turns out to be related to having the first component have the only polar term in Q. So you have the first component has a Q to the -1/4m, and then all the other components are well behaved as tau goes off to I infinity. So you look for Jacobi forms satisfying that condition, and if they exist, they're unique. And in some cases, one can prove, sort of in the untwisted case, the AN systems, you can prove that the list that we have here are all the possibilities. But more generally, I think there's a classification problem which is not completely solved. There's also a completely different point of view which has been developed in work of Miranda and John separately and before this, which uses which involves Rademacher summability and allows one to actually construct a lot of this numerically. So a lot of our work involved doing analytical manipulations and comparing them with numerical results, which you get by this Rademacher thing where you approximate these, you have some finite number of sums, you terminate it and you do it numerically and you compare the two. And we often found that we'd missed things using one technique that we found using the other, and the cross correlation allowed us to get a lot of data. So we had to use a lot of tricks and underhanded things to construct the Mach modular forms. And I think that there's a missing idea someplace that tells you more directly how to get at them.